So moving on to question 5. For question 5 you're immediately presented with a passage of text and a graph to look at. And with all these questions it's very important to make sure that you read through the information carefully to begin with. In the passage of text it tells you that scientists were investigating the effect of iron deficiency on the production of triose in sugar beet plants. Now, a deficiency is a situation where you've not got enough of something. If you have a vitamin deficiency, you don't have enough vitamins in your body. In this case, we're looking at the effect of not having enough iron in the production of triose in sugar beet plants. Now, since this question refers to triose, you should immediately recognise that the question is about photosynthesis, because triose is produced in the light independent stage of photosynthesis. The question goes on to give you some details about the experiment, and it tells you that the plants were all grown under the same conditions for a period, and then 10 days before the experiments, half of the plants were transferred to a growth medium with no iron. So half of the plants were put in a situation where they didn't have enough iron. The scientists then measured the concentration of triose in these plants, and in the control plants that presumably did have enough iron. If we look at the results from this experiment, on the x-axis along the bottom here we've got time, and we've got the 16-hour period, and then on the up-axis, on the y-axis, it shows us the mean concentration of triose. In the control plants you can see the concentration went up very rapidly and then levelled off, whereas in the plants that were iron deficient there wasn't so much triose produced. Let's look at some of the questions then. So, the first question we have asks us why the experiments were carried out at a high carbon dioxide concentration. Now, in this experiment, the scientists wanted to investigate the effect of iron deficiency on triose production. So they don't want the effect of carbon dioxide spoiling their experiments and affecting their results. This is an AQA exam, however, so we're not going to get away with explaining this without using some key words. Now, we do know a key word, or a key phrase at least, that refers to how carbon dioxide can affect the rate of photosynthesis, and that phrase is limiting factor. So we're going to make sure that we put that phrase limiting factor into. So this is the answer we've come up with, and we're saying that carbon dioxide concentration is not the limiting factor. The scientists, as I've explained, don't want carbon dioxide to affect their experiment, so they want it not to be a limiting factor. Next we have this question, which asks why it was important to grow the plants under the same conditions for up to 10 days before the experiment. Now, when you do an experiment like this, you want to make sure that any differences you see are due to your independent variable, which in this case was the amount of iron available to the plants. So the answer that we need to put is something that explains that by making sure that the plants were grown under the same conditions for up to 10 days for the experiment, we're making sure that the only differences we see in triose production are due to the differences in iron. We've got one more question about the way the scientists have set up the experiment. Now, in the method it tells you that before the start of this experiment, where they've been measuring triose production, the plants were left in the dark for 6 hours. Now, the reason the scientists have done this is to make sure that all the plants were absolutely in the same state before the start of the experiment. When plants photosynthesize, they produce triose, and if you've got a set of plants, some of them might have slightly more triose than others at the start of the experiment. Again, that could affect your results and make your experiment less valid. By keeping the plants in the dark for 6 hours before the experiment, the scientists are making sure that all the plants basically have no triose left, or have a very low amount of triose left, and then they can be sure that any increase they see on their graph or in their results is due to what's actually happening during the period of photosynthesis that they are actually measuring. So our answer would look something like this. The plants were left in the dark for 6 hours to make sure that all the plants had the same low level of triose. So, those questions are all to do with how the experiment was set up. Moving on, we've got a slightly easier question, I think, which is about how iron deficiency affects the production of triose. It tells us that iron deficiency reduces electron transport. It then asks us to use this information and your knowledge of photosynthesis to explain the decrease in the production of triose. Now, this question is asking us to use our knowledge of photosynthesis. And we've got to link that to the statement that iron deficiency reduces electron transport, and use that to explain how triose is stopped from being produced. Electron transport, you'll hopefully remember, takes place in the light-dependent stage of photosynthesis. And if you think back, we spent a long time looking at how light energy was used to excite electrons, then pass through an electron transport chain in the thylakoid membranes of chloroplasts during the light-dependent stage. So we need to explain that if there's less electron transport, that's going to affect that process, or the processes that take place in the light-dependent stage. We've got to link that to triose phosphate production. Now, if you remember your work on the light-independent stage, you remember that triose phosphate production requires glycerate 3-phosphate, or GP, being reduced to form triose phosphate, or TP. That process requires ATP, and it requires reduced NADP. Now, those substances, the ATP and the reduced NADP, are produced during the light-dependent stage. So, if you prevent electron transport, you're going to prevent the production of ATP and reduced NADP, and as a result, you'll stop all the processes that require those substances. So I've put the answer up on the screen there, and it follows pretty much what I've just said. Now, in the mark scheme for this question, there was a mark for remembering that ATP and reduced NADP were required, 1 mark each. And there was a mark for remembering that those were required for the reduction of glycerate phosphate. The final mark was for mentioning that these took place, the production of these substances, ATP and reduced NADP, took place in the light-dependent phase. For the final question then, it says that iron deficiency results in a decrease in the uptake of carbon dioxide, and we've got to explain why. Again, we need to look back at our knowledge and our understanding of photosynthesis, and hopefully you remember that carbon dioxide is taken up in the light-independent stage, and it's combined with ribulose bisphosphate, RUBP. So, if there's less uptake of carbon dioxide, that must mean that less RUBP is combining with carbon dioxide. Now, we've got to link that to iron deficiency, and we know that iron deficiency results in less GP being converted to TP. So, that must somehow result in less uptake of carbon dioxide. Now, the answer to this is that because TP is required to regenerate the RUBP, by reducing the production of triose phosphate, there's going to be less ribulose bisphosphate available to combine with carbon dioxide. So the answer should look something like this, 1 mark for each point.